Okay. So you're going to open up a Sigwin terminal,
Okay.
which will look similar to this.
Yes.
To log on to, so the name of the computer is Davros.
Okay.
Don't know if you're a Doctor Who fan, but
I've watched a few episodes.
Okay. It's a Doctor Who reference. Anyway,
More
so
of a Star Trek fan.
yes, I also am as an aside. I'm recording all of this now, so this is good. So this is all very highly relevant. But I seem to have got about 5 students rewatching Voyager at the moment.
That is my
which
favorite
I'm
one.
very happy about because
Yeah. I started
Because
with that one and then I was disappointed with all the other ones.
Yeah. Okay, so to log on to the computer, you use the command SSH-L. So SSH just stands for secure shell. A shell is just the technical name for the environment, the Linux environment.
Okay.
-L just means login, and then your username is Preston, and then the name of the computer is Davros, and then it'll ask for your password. At the moment, you've been given a temporary password. Set REB, which means, yeah, it'll ask me to change it. So I'm just gonna make up, not make up, but I'll give you a password for now. Let's make it. Oh, that was the code. I hate it when it does that. Okay, so here I'll write down the password that it's capital M, lowercase e, $3110, capital D, lowercase e, K.
Okay.
That doesn't mean anything. It is that's actually a combination of passwords that my PhD supervisor used to use. And when she first set me up on computers, she used passwords that so this is like a 20-year now sequence of passing on
passwords
and slightly just like splicing them together, and so
nice.
Okay, so you'll type this in, enter that password, and then you'll be on Davros, and you currently have nothing there. So let's let me go over to my account. Yes, I do. Oops. Okay, so Okay, so there is a this is a directory here, GNSProp single.
Okay.
GNSProp just stands for General Neutron Star Properties. That's the name of the code.
Okay.
So to for Linux, the basic, you need to know a few basics about navigating around. So, for example, to list everything in your current directory, it's just ls,
Okay.
and that lists everything. If I want to then enter a directory in the directory I'm in, such as this one here, then I do cd, which means change directory.
Okay.
And then the name of the directory. A useful trick with Linux is if you so there's only one directory that begins with the letter G.
Mm-hmm.
So if I hit tab, it automatically it auto completes it because it knows that must be what I mean. So that just speeds things up. Okay, now let me see. Which version this is. So this code is written in Fortran 90.
Mm-hmm.
But you don't need to start learning that yet.
Okay.
We'll see. Once we figure out the details of the project, we may or may not need to modify the code. But at the moment, it should be set up to run already. So what it does is it takes, so this eos.dat is the equation of state. And it's just this table that has, this left column is density in units of grams per cubic centimeter.
Okay.
Then the middle column is pressure.
Okay.
And the right column is baryon number density. And it goes from the highest density downwards to the lowest density. So it spans again, neutron stars span a huge range of density. So it starts, at the lowest densities, the outermost part of the star at 10 to the 4, which is still really dense. 10 to the 4 grams per cubic centimeter, and then goes up to the ridiculous densities of 10 to the 15 grams per cubic centimeter. And then the pressure is in units of, so regular, do you remember the regular SI units of pressure?
No.
It's pascals.
Pascals, okay.
Yeah, which is just a Newton per meter square.
Okay.
Because it's force divided by area.
Mm-hmm.
But as I think I mentioned a couple of weeks ago, neutron star astrophysicists work in CGS units.
Right.
And the unit of force is in CGS is the dyne.
Okay.
So for regular meters, kilograms, second, force is in newtons, and for CGS it's in dynes, which doesn't have that much of an abbreviation. but it's just because a Newton is a kilogram meter per second squared.
Okay.
So a dyne is just a gram centimeter per second squared.
Okay.
It's just the equivalent. And so this pressure here is, the units of this second column is dynes per square centimeter.
Okay.
Again, to give you a reference point, atmospheric pressure, 1 atmosphere, is about 10 to the 5 pascals. Let me just double check that. I'm now doubting myself as I say it. Yes, okay, yeah, phew. So, just check. So 1 atmosphere is 10 to the 5 pascals, that's 10 to the 5 newtons per meter square. That's 10 to the 5. So a newton, I can't remember it off the top of my head, so I always have to do the conversion every time. So a newton is a kilogram meter per second squared.
Yes.
Yeah, and then I'm dividing by meters squared. So that cancels that. So then I need to convert kilograms into grams, and a kilogram is 1,000 grams, so that bumps this up to 10 to the 8 grams per second squared meter. And then I need to convert meters into centimeters, so that's, a meter is 100 centimeters, so that's 10 to the 6 grams per second centimeters, which is 10 to the 6 dynes per centimeter squared. Okay. So the pressure here is 10 to the 30 times bigger.
That's insane.
Yeah.
Okay.
How low does it get? It goes down to 10 to the 18. That's only, yeah, it's reasonable. It's only 1,000 billion times Earth's surface. Anyway, and then the baryon density is just that's another way of writing density.
Okay.
So like this, so this is mass density, so amount of grams per cubic centimeter. Baryon density is number of baryons per cubic centimeter, so just the number of particles, the number of neutrons and protons in a cubic centimeter.
Okay.
So it's just, yeah, number of neutrons or protons in a centimeter cubed. So it goes up to about 10 to the 39, which is large. And again, to put it in context, in normal densities, the number of things, atoms or neutrons and protons per cubic centimeter is roughly going to be Avogadro's number, which is 10 to the 23. So it makes sense. So this actually tallies with that, because this is about 10 to the 16 times larger. And this density here is about 10 to the 16 times larger than the density of water, which is 1.
Right. Okay.
So, yeah. So a normal baryon density in ordinary circumstances would be about 10 to the 23, 10 to the 24 baryons per cubic centimeter. Okay. Then, by the way, this I'm using this command vi.
Okay.
So vi is an editor. So if you just type vi and then the name of a file, it'll open it up and you can edit it. I will. Vi is really, really quick to use once you get used to it.
Okay.
But it's completely counterintuitive and therefore takes a while to get used to.
Okay.
The commands are just the way you edit stuff in it.
Okay.
Is not like most text editors.
Okay.
So because you can navigate around like this. To insert stuff, you have to enter in an insert mode. You type I, and it says insert here. Now I can, if I wanted to, insert lines. Right.
Okay.
And then I hit escape to get out of insert mode. To save my changes, I do capital ZZ.
Okay.
Which doesn't make sense, but that's what it is. If I want to exit without saving changes, I do :Q exclamation point.
Okay.
It's the most user-unfriendly set of commands. Luckily, millions of people have put together VI cheat sheets because everyone knows that it's terribly counterintuitive. So there are a million of these VI cheat sheets out there that can see some of the things I just mentioned here. Capital ZZ and :Q exclamation point, and then other things. But despite that, it is very quick and easy to use. It's not good if you want to make big changes to a file, but if you just want to tweak
a few things,
it's fairly straightforward. And then if you haven't made any changes, then :Q exits. And you've got there's an input file called input.dat, and the main thing that you will the only thing you need to worry about here is that this or know about is that this fourth line here. So this tells me what mass of star I want to start at.
Okay.
And it tells, so basically this line says I'm going to start with a 2.5 solar mass neutron star, and then I'm going to start going down in mass, and I'm going to go down 36 times, each time subtracting 0.05 solar masses off.
Okay.
So that will leave me 36.05 is 1.8. So it'll leave me down at 0.7.
Okay.
So solar masses. So this will create it tells it to do is make 36 neutron star models with masses starting at 2.5 and going down.
Okay.
To execute the code, the executable is GNSProp. So by execute, that's just the thing that you run, and to execute it, you just type /GNSProp, and it'll start running, and there it goes. Now it turns out that this equation of state has a maximum mass of 2 solar masses.
Okay.
We told it to start at 2.5 solar masses, but it can't do that because the equation of state doesn't allow for neutron star models that high. So it automatically cuts it off at 2 solar masses. So it's run models from 2 solar masses down to 0.75. Now we've got a load of output files, one for each of these neutron star models. Actually, there are a few different output files, but each one has a version for each neutron star model.
Okay.
And then there's an overall, the thing that I think we should start looking at first is just this one output file, nssequence.out, which contains details of just the summary details of the models that we just ran. So if we look at that, so this column is the mass from 2 solar masses down to 0.75. There's slight rounding errors just because it's there's only a finite accuracy.
Right.
But and then the third column here is the radius in kilometers.
Okay.
And the let's see, trying to remember which column is which. I think this one is the gravitational mass. Sorry, no, this is the gravitational mass. This is the baryon mass.
Okay.
The difference is that the gravitational mass is the mass we would measure.
Mm-hmm.
But the one of the many weird things about general relativity, I guess it's weird, is that energy contributes to gravity as well as mass.
Mm-hmm.
So you can have, if you have a 1 kilogram object at rest and a 1 kilogram object moving at 1,000 miles per hour,
mm-hmm.
the 1 kilogram object moving at 1,000 miles per hour has a higher gravitational field, because in addition to its mass, it has a kinetic energy,
mm-hmm.
and that contributes to its gravitational field.
Okay.
So neutron stars have huge amounts of gravitational potential energy.
Okay.
In fact, they have, and gravitational potential energy is negative. So what this is the mass in solar masses of. This is what you would get if you took the neutron star apart, one proton and neutron at a time,
mm-hmm.
and weighed each one individually.
Okay.
And added it all up, you'd get 2.36 solar masses.
Okay.
So that's the individual mass. That's the total mass of all the individual constituents.
Okay.
But when placed together in a neutron star, they also have a gravitational potential energy, and that actually reduces the mass, the mass we measure, by a whole third of a solar mass.
Okay.
So we measure the neutron star to be a third of a solar mass lighter due to its potential energy.
Okay.
Right, which is quite astonishing because, to put it into context, the sun weighs 1 million times as much as the Earth.
Yeah.
So
that's a lot.
So a third is 300,000. So there's 300,000 Earths worth of gravitational potential energy that a neutron star has. So I think that a good place to start would be to run this code a few times for a few different equations of state, and then try plotting the mass versus the radius in Python. So what you would do, so if you once you've run it through an equation of state and you've got this output file, then you want to copy it back to your laptop.
Okay.
And then you can plot it locally.
Okay.
So what you do to do that, you first need to exit davros.
Okay.
And then you go to whatever directory you want to store the results in. So you'll create some directory to keep things in.
Okay.
So they're all in one place on your laptop. Okay. So you can create a directory, and then to copy files from davros to your laptop, you use the command scp.
Okay.
And the way this works is you do scp, then your username at davros : and then the location and name of the file. So it's in directory GNSProp, and the file's name is sequence.out. And then you need to tell it where you want to copy it to. If you're in the directory where you want it to be, then you just do dot. And then you enter your password. And it'll copy it there. So I've just copied it to my desktop, so it should appear. There it is. So I'll create a directory. Okay, and then I will send you an example of a simple Python plotting code. I don't think I did that, did I? No. To get you started.
Okay.
Let's see if I can find one quickly. I'll need to tweak this, but that'll give me the opportunity to show you how it basically works. So let me get rid of that. So I think have I talked about Python at all?
Not really.
No. So the basic way, the nice thing about Python is that there are, for pretty much everything you ever want to do, there are already packages written and functions written that can take care of it for you. So when it comes to, so for example, when it comes to just doing basic mathematical functions, there's this package called NumPy. And then when it comes to plotting things, there's a package called Pylab and another one called Matplotlib.
Okay.
So there are thousands of packages. So what you do is every Python code starts off importing whatever you need to use.
Okay.
Often there are functions that have the same name in different packages. So sometimes you want to use some shorter name or different name for a package. And if you want to do that, you say import whatever as, and then give it whatever you want to call it.
Okay.
So pyplot is a function that plots two things, and I've imported it as PLT here,
Okay.
just because it's shorter to type. this line you don't need to worry about. This enables LaTeX, so it enables you to be able to type, to easily put equations and Greek letters and things on your graph. So here's where the crux of it is. What we want to do is we want to, let me open this file. So we want to plot the mass versus the radius, okay, from this. So we want to import the third and fourth columns of this.
Okay.
Now, okay, so we're importing it from, so this command is, so NP stands for NumPy, so load text is a function in the package NumPy.
Okay.
So the way Python works is you say what is the package you're using, and then dot, and then the function you're using from that package. Okay. And you then just give it the name of the file you're going to read the data in from. This is the variable, whatever you want to call it, so let's call it mass.
Okay.
Mass is the fourth column, but Python starts counting from 0.
Okay.
So it's 0, 1, 2, 3.
3.
So you say useCols equals 3. Then radius, you do the same thing. This is the second column. And then you just do plt.plot. And then mass. These are just your x and y variables. Actually, radius is x. And then again, a lot of this is self-evident. Color is the color of the plot. Label is what you want it to be called if you want to display a legend. So if you have multiple lines and you want to distinguish them, so let's just call this EOS test. These are the limits on the x and y axes. Okay. So our x is going from, let's go from 0.5 to 2.5, and our radius goes from about 9 to 12, so we want to make it the limits a little wider than that, so let's go 8 to 13. Then these are the labels. So x label is going to be radius in kilometers. Y label is going to be mass. And this is where this command comes in handy. Okay. So the symbol for mass of the sun is m with a subscript of the circle with a dot in it. Yeah. So to make that appear, you enter $enters so-called math mode in LaTeX. Okay. Actually, yeah. In LaTeX, underscore tells LaTeX to do a subscript. Okay. And then whatever the subscript is needs to be in curly brackets. Okay. And the symbol, the O with a dot in it, is called O dot.
O dot, okay.
Yeah. LaTeX is also nicely intuitive in its commands, fortunately. And then $ends math mode. Okay. And then font size tells you how big you want the labels to appear. And then this draws the graph, and then this saves it as a PDF. Okay. If you want to display the legend, then it's just plt.legend. Okay. And you can then, there are other things you can tell where you want the legend to appear on the graph. Okay, so wrong one. So in Anaconda, typically what you'll do is you'll open this up in Anaconda,
Okay.
make sure that this code is in the same directory as nssequence.out.
Okay.
And then in Anaconda, I think there's like a run button that runs the code.
Okay.
I'm going to run it because in Mac it's just easier to run it in Linux. So in which case, yeah. I think you can open up a command line like this in Anaconda as well. So you can also run it like this.
Okay.
And you just do Python, whatever the name of the code is. This is an example plot. So you run it, and this is just a warning, luckily, so it's not an error. This is just saying there's some feature that's been is now obsolete.
Okay.
It still recognizes it. Okay, so now if we go to the directory, we see we've got the graph and nothing has appeared in it, which means we've done something wrong. So this is oh, that's right. I've got my limits the wrong way around. Just swap this. It's y, x. Here we go. Oops. Need to close it.
Okay.
So there you go. So it's plotted the results.
Okay.
There's your mass radius curve. So it shows the legend.
Mm-hmm.
So that is basically how it is done. So what I'll do is I'll send you a few other equations of state so you can run it a few times.
Okay.
You can plot them all on the same graph. You can essentially so for example, if I just to show you an example of plotting more things on the same graph, if I read in the baryon mass, which I think is column 5, then I can just add a second plot statement where this time it's B mass. And there you go.
Okay.
So it's once you get used to it, it's very easy and powerful to use.
Okay.
And you can create plots that look much better than, say, equivalent plots. So it's easier to use than things like Excel.
Okay.
Once you get used to it,
mm-hmm.
and the plots look
nicer,
much nicer. You can, I mean, this is just a very simple code. You can tweak things. So this is just an example. This is gravitational mass, baryon mass, and to distinguish so they're both solid line curves,
mm-hmm.
but you can make dashed lines or dotted lines by I think it's line style. Yes, it is acceptor. Yeah, there we go.
Okay.
Always close it before it.
There we go.
Yeah, and there's a whole variety of, you know, all your usual plotting or types of plots you can do. So so plot does a line plot by default. You can just as well do a scatter plot, in which case I won't need that. So it just plots the individual points instead of joining with a line, and it's very easy to adjust things like colors, and it's all fairly intuitive. And the best thing is it's very easy to Google what you want it to do. If you want to do anything, essentially, if you just Google what you want,
it'll tell me.
You know, someone will. You could essentially, you'll be able to cut and paste from something someone's done.
Okay.
So.
Okay.
And the final thing is just to let me just log back onto your account on davros. Go back to here. So I'll send you a few more equations of state to play about with.
Okay.
The code looks for, will just read in whatever's called eos.dat.
Okay.
So I'll send you a bunch of others that'll have different file names. So for example, let me just change the name of this. So I might send you some, you know, maybe it'll be called eos1.dat.
Okay.
It won't, it'll be called something else, but just right. But GNSProp will not recognize that. It's looking for eos.dat.
Okay.
So what you need to do is you do CP, which is just copy the whichever equation of state you want to run, and then eos.dat, which is the.
Okay.
And then you run it, and then you'll copy the next equation of state to eos.dat, run that.
Okay.
What you might want to, or what you definitely will want to do is, so each time it'll overwrite the results from before.
So I want to save them.
So you need to save them somewhere. So to create a directory, you do mkdir, make directory.
Okay.
And then whatever you want to call it, so EOS1 say, and then you'll see there's EOS1 has appeared there, and then you can move, and you want to move all of the output files from EOS1 to this directory.
Okay.
Now, of course, if you go through one by one, it's going to take forever. Luckily, Linux has or supports the use of wildcards, which are things like star. So I can do star.out, and that will select every file that ends .out.
Okay.
And then I move it to EOS1, and you see they've all gone because they're now in there. And now I can run GNSProp again with another equation of state.
Okay.
And my previous results are safe in there. So I'll just
Okay.
create a new directory for each equation of state.
Okay.
Okay. So again, I'm sure you'll, inevitably there'll be questions.
Yes.
And there's a lot. But I will send you this video.
Okay. Perfect.
Apologies that it's quite rambling, but
It's okay.
But you can at least fast forward through to whichever bits you need. I'll send you the equations of state, and then just have a go at starting to run the code.
Okay.
And at any time later this week, if you run into problems or
Okay.
whatever,
Okay.
I can help if necessary.
Awesome. Thank you.
No problem.